Next, we will look at some properties of the potential flow motion, potential motion, irrotational motion, and we will use those to build a framework through which we can develop a solution. So of course, you can always solve for del squared phi equals 0 with appropriate boundary conditions, okay? And that's completely a legitimate way of doing this. You know the boundary conditions, you know your domain. But however, we notice that one key feature of this operator, the Laplacian, is that it is linear. And so you can say that the Laplacian operator is linear. Okay, so what does that mean? What does that mean? So if phi1 is a potential such that del squared phi1 is equal to 0, phi2 is a potential such that del squared phi2 is equal to 0, and then phi3, again, del squared phi3 is equal to 0, then we can say that phi, defined as a linear combination of phi1, so a phi1 plus b phi2 plus c phi3 plus d, where a, b, c, and d are constants, then this phi is also a potential. This is a pretty cool result because del squared phi is equal to a del squared phi1 plus b del squared phi2 plus c del squared phi3 equal to 0. So this gives rise to the idea that you can superimpose different potential flow solutions. So for example, and we will see this later, the flow over a cylinder, which is sort of given by something like this. You have what looks like a cylinder, and then you have streamlines around the cylinder, etc. This is given by the superposition of uniform flow. Let's use here uniform flow plus flow over a plus doublet flow. So uniform plus doublet, where it's a source and a sink at the same time. It kind of looks weird this way, but then you superimpose those two and you get the flow over a circular cylinder. Okay, so this is a pretty cool feature. We will see how we're going to do this. So therefore, we can develop basic building blocks of potential flows and combine them to obtain more complex flows. This is a pretty cool feature of the irrotational motion and the velocity potential. Okay. The second thing that we will do is, if we go to 2D, if we focus on 2 dimensions, then we can also use the stream function. So why do we want to use the stream function for the simple reason that the stream function is a little bit more intuitive than the potential. So for example, if I ask you to give me an idea of what the flow through a backward facing step channel looks like, you'd immediately draw lines like this. You're just going to draw a line over here, and then a line over there, and then a line over here, right? And a little recirculation here maybe, and this kind of line. So naturally, these are the streamlines because they're that's what the velocity looks like, right? So we naturally think in terms of the stream function, and those are different streamlines with different values, C2, okay? But what about the velocity potential? We kind of have no idea what that looks like. It's really not that intuitive. Well, it turns out that in 2D, in two dimensions, only in 2D, phi, lines of constant phi, is perpendicular to psi. So that's a very interesting fact. So in this case, the potential lines would look perpendicular to the streamlines. Okay, they kind of look like this. Okay, and each one of those is a phi, value for phi. We call those the equipotential lines. And we'll prove this right now. So if you restrict yourself to Cartesian coordinates, we have u is equal to d phi by dx, and that's equal to d psi by dy. And v is equal to d phi by dy, and that's equal to minus d psi by dx. So now, just as an aside, to show that two lines are perpendicular, if and only if their slopes, the product of their slopes, the product of slopes is -1. So if you have ax plus b, cx plus d, these two lines are perpendicular if a times c is equal to -1. So it's sufficient to show that the slope at a point, the slope of a streamline times the slope of a potential line is equal to -1. And so let's do this. D phi, which is the total change in on an equipotential line, is d phi by dx plus d phi by dy. That's equal to 0. So this is u dx plus v dy equal to 0. And this implies that dy by dx, which is the slope, that will be minus u over v. Okay, so this is for the potential. For the stream function, d psi is d psi by dx plus d psi by dy, and that's equal to 0 because psi is constant along a streamline. So think of this as a streamline and a potential line. I know they will be perpendicular, okay, but just kind of drawing them right here. We haven't shown this yet, but we're looking at this point, we're looking at the change in phi and then the change in psi. This is psi and this is phi, okay? And that's equal to v dx minus, so minus v dx plus u dy equal to 0, and therefore dy by dx is equal to v over u. Now you combine these two, dy by dx for phi times dy by dx for psi, that's equal to minus u over v times v over u, and that's equal to -1. So this is only true phi perpendicular to psi only in 2 dimensions. Okay, so in 3D you can't define the stream function. It gets really complicated if you define it in 3 different planes. But also in axisymmetric flow, we will see that later, axisymmetric flow, phi is not perpendicular to psi. Okay, so this is just gives you an idea of really of what phi is. Okay. Okay. So now we're going to use both phi and psi for the building blocks that we discussed. But first, let's ask ourselves: so what is the governing equation for psi for a potential flow? So for potential flow, remember, potential flow, omega, we're going to put c, the only non-zero component, is equal to 0. For the velocity potential, if u is equal to grad phi, this implies that div u is equal to del squared phi is equal to 0, and that is sufficient to determine phi. But for psi, div u is automatically satisfied. So div u is not going to give us an equation for psi. And even if we substitute for psi in the momentum equations, you still have the pressure. So which equation do we use to get psi? Well, it turns out that we haven't used omega equals 0. If you remember, omega z was curl u dot ez, which was the last curl u, and you take the only non-zero component, and we showed earlier that in 2D this is equal to del squared psi, but omega z is 0, and therefore also del squared psi equal to 0. So therefore both phi and psi satisfy Laplace's equation in 2D. Okay, del squared psi is equal to 0. This will not be the case for axisymmetric flow. We will show this in a second. The Laplacian will always hold true for the potential, but not for the stream function under different coordinates. So let's look at what these equations look like in Cartesian coordinates, straightforward. So if we do Cartesian coordinates, we have u is equal to d phi by dx, and that's d psi by dy, and then v is equal to d phi by dy and minus d psi by dx, and del squared phi is d2 phi by dx squared plus d2 phi by dy squared is equal to 0, and del squared psi, same equation, d2 psi by dx squared plus d2 psi by dy squared is equal to 0. For polar coordinates, which are 2D, polar coordinates are theta. The same is true. We have ur is equal to d phi by dr. Remember, u is grad phi or curl psi. So that's how you get these components. 1 over r d psi by d theta, and u theta is 1 over r d phi by d theta, and that's equal to minus d psi by dr, and the Laplacian is the standard Laplacian. Del squared phi is equal to 1 over r d by dr, r d phi by dr, plus 1 over r squared d2 phi by d theta squared equal to 0, and del squared psi is the same thing. Del squared, just put psi in here, it's the same equation. And you can double check that you get this del squared psi is if you simply just compute omega z is equal curl u in this case. And finally, we're going to look at axisymmetric coordinates. So axisymmetric flow is not really two-dimensional because you still have changes in the z direction, and so that's going to be a little bit interesting of a flow. And the way we formulate this axisymmetric flow, so one way to visualize this is if you consider like a body of revolution. Looks like kind of like this. And you have the z-axis aligned along this direction, and you have x, then you have y, and r and theta. So this would be r along this line, right? This would be r, and theta would be in this direction. Okay, so it's the angle made with the x-axis. Okay, theta, and the flow in this case looks like this, right? Goes around the body, and that's axisymmetric flow. So in this case, yes, we know that d by d theta equal to 0, but we will see that the Laplacian holds for the velocity potential always, but doesn't hold for the stream function. The stream function will end up getting a different equation for the stream function. So ur is d phi by dr in this case, and that's equal to minus 1 over r d psi by dz, and uz is d phi by dz, and that's equal to 1 over r d psi by dr, and the Laplacian del squared phi in this case is 1 over r d by dr r d phi by dr plus d2 phi by dz squared equal to 0. However, del squared psi is not 0. Instead, we have to derive the equation for psi from omega z equal curl u equal to 0. And so if we do this, curl u in this case is dur by dz minus duz by dr equal to 0, and simply substitute ur and uz, so we get d by dz, we have a minus sign from this guy of 1 over r d psi by dz, we have a z over here, okay, minus d by dr, and uz is 1 over r d psi by dr equal to 0. If we multiply by a negative sign, this gives us d by dr of 1 over r d psi by dr plus 1 over r d2 psi by dz squared equal to 0, which is not the Laplacian. Okay, so be very careful. Only in 2D the Laplacian holds for both the stream function and the velocity potential.